Hello and welcome to this video. In the last video, we started designing an FSM, and this is what the FSM will look like. It's called FSM1, and it's going to have two components, clock FSM and a ring counter on the inside. So this is our overall architecture we want to come up with. First of all, we want to focus on the clock FSM entity to get that out. Once we have that sorted out, we'll focus on the ring counter. Once we have the ring counter out, then we'll put everything together and have our FSM1. So let's go on with the architecture. We came as far as declaring the entity, and then we started out the architecture. So I'm just going to take it from here. Now, I decided I don't want to have just one state. So I should say the reason why I'm doing this. Now, there are three ways we could encode FSMs in VHDL. We could use the one process method, the two process method, or the three process method. In the one process method, we have just one process defining the entire FPGA. In the two process method, well, we use two processes. In the three process method, we use three processes. Now, I personally use the three process method, and the reason is this. With a three process method, you have three processes. One determines what the present state is at any point in time. So all that state does is, whenever an active clock transition comes in, remember we said every FSM has a clock. Whenever there is an active clock transition, it asks the question, what should be the present state now? And it simply sets the present state on every active clock transition. That is what the first process does, or that's what one process does. Usually we put it as the first process. Another process is dedicated to just determining what should the next state be. Based on the inputs I have right now, based on the present state I have, what should the next state be? Okay, so that's what the second process is focused on. The third process says, okay, based on the state I am in right now, what should the output be? So now this obviously works well for a more machine, so I'm describing this for a more FSM. So based on the present state, what should the output be? And so having those three different processes is good, particularly when you have a complex project. With a complex project, you sometimes want to come back later to add new features or to take a feature away, to adjust something. It's a lot easier when you have three separate processes, such that if what you want to tweak is the output logic, then you know which process to focus on. Just focus on the output logic, and that is all you're bothered about. On the other hand, if you want to focus on the transition logic, what causes it to go from one state to the next state? In other words, what causes it to determines what the next state will be? The logic that determines what the next state will be, you can look at just the process that talks about transitioning. On the other hand, usually you will not need to look at the other process that simply talks about what the present state logic will be. So let's go ahead and do it this way. Now, in order to do this, I'm going to actually need two signals, not just one signal. Here I have one signal called state, but rather I want to have two signals. One that holds the present state, and another that holds what the next state will be. Okay, so we have present state and the next state. So let's go into our code. First state will be the present state, if you want, logic. So I've got a present state logic or present state process, anything you want to call it. I'm good with that. So process, and this is dependent just on the clock and reset. So begin, end, process. Now, whenever, okay, begin. Yeah, I can still spell, good. So whenever the reset button is pressed, then we want to go to the reset state. So if reset is equal to 0, okay, so if reset is low, then I'm using reset is low because on the DE10-Lite board, and if on the DE10-Lite board, the push button is high by default. When you depress it, in other words, when you want to make it active, you make it low. So when we press the button, at that point it goes low, and that is the point I want to detect. So when reset is low, remember this logic is just to determine what the present state is. Then the present state is equal to 0, 0. So that's what the present state is, because that is our reset state. Else, if reset button is not being pressed, then we are now interested in the clock. So we check if we have a rising edge of the clock, and if we have the rising edge of the clock, then we need it then here. If we have a rising edge of the clock, then we can make our present state next state. And that is it for this process. Generally speaking, in a three-process setup, this will always be one process. Your present state logic will always be this. It will never look different from this. So if you want, you can keep this and just copy it and keep it somewhere. You will always use this. Now, on the other hand, next process, I'm going to make it the state transition logic. Again, you can put them in any order. You know that. It really doesn't matter what order in which you put this process. Now, this determines how it will transition, what will make it transition. So this is not dependent on clock. Rather, this is dependent on the button, because when it's in a present state, then the button makes it the button makes things transition. So it's the sensitivity. I'll have button in there. Begin end process. Okay, so in here, the easiest way to do this is to use a case structure. Okay, use a case structure. You could use if statements, but a case structure is a whole lot easier. So, or at least it looks better. The format looks better. So we're going to have a case statement and case present state, because the present state we are in is what determines is. So I'm going to put my present state in my sensitivity list in here. Present state. Okay, so I'm going to put it also in my sensitivity list. So case present state is, it checks the present state and then it checks what the button is. I hope that makes sense. So we are looking at different present states. If it's in a present state, if it's in this particular state, then the button causes something to happen. The input causes something to happen. If it's in another state, the input causes something else to happen. But remember, all we are focused on here is what makes it transition to the next state. What is the transition going to the next state? What's the transition? What's the next state it is transitioning to? So present state is when the present state is 0, 0. Then we're going to have some pieces of code over here. Let me just go ahead and duplicate this a couple of times, because we're going to have 4 states in all. So when it is 1, 1, when it is 1, 0, when it is 0, 1, and when it is 0, 0. Okay. So each one of these, you will have some code going down here. And I'll go ahead and put one more state, and that last state will be, say, when others. Now, the reason why it's always a good idea to have when others is that we are using standard logic. Okay, so our signal present state is standard logic, is of type standard logic. That means it can have a value of high, it can have a value of low, but also has a possible value of unknown, high impedance, weak high, weak low, strong high, strong low. So the point is that it can have 9 different values. All we have dealt with are 4 here, are 2 different values, high and low. And so we've dealt with 4 different states. So let's have a when others. And if there's any other state, then maybe we'll give it the same thing that it has in the reset state. Okay. So if we're in the reset state, which is state 0, 0, in the reset state, what do we want to happen? Well, we want the next state at any point, once we're in that reset state, automatically transition to the next state. Let's come to our figure. Don't just take my word for it. This is the diagram we had. We said once we're in this reset state, then definitely transition to that state. We'll talk about the output in the output process, but for now, always transition to this state. So what I'm just simply saying is, once we're in that state, then next state will simply be equal to 0, state 0, 1, and that will be that. It will be equal to state 0, 1. So I'm going ahead and just take this and say, if it is in any other state, then transition to state 0, 0. Okay? If it's any other state, then transition to state 0, 0. And that's that. So we're good. Okay? So I think we're good here. Now, next thing I'm going to do is to go ahead and deal with all the other states. And it's occurring to me that we might have a slight challenge in here. So let me go ahead and encode this, and let the error pop up, and then we'll fix it. Okay, so if an error does pop up, we'll fix it. But I think an error will pop up at some point in time, but let's just leave it be. Let's go ahead. So if our button, we want to check if the button is pressed, and okay, so we want to check if the button is pressed, and if the button is pressed, then sorry, just give me one moment. I'm in my head asking the question that I want to do. Okay, so should I go ahead and do it this way? So let's do it this way. Let's try to avoid any errors. So before this, because I'm asking myself, should I do this since this is the first FSM? So let me go ahead and write my code in one way. I'll change it later on, okay, to another way. So now if I know that what we said here was that we should transition on rising edge of button, but I'll not transition rising edge of button just because I know it's likely to give an error. So rather, if button is equal to high, I said this to give a problem. Let's see that problem in there. So if button is high, then and if button is high, then next state in state 0, 1 should simply be equal to state 1, 0. Okay, so if button is 1, then I haven't put my equal to. How did I miss that? Okay, so if button is 1, then the next state will definitely be state 1, 0. What if it is not? So let's think about this code so far. At some point in time, this process runs through. Present state is 0, 0. Next state is set as state 0, 1. Now when the state, next state is set as state 0, 1. When that happens, then at the next active clock transition, your present state becomes that next state. So once this has happened, on the next active clock transition, your present state will become that next state, okay? And so both of them will now be 0, 1. So next state is 0, 1, present state is 0, 1. So we now enter this case. When present state is 0, 1, then it now starts checking the button. If the button is 1, then your next state automatically is now set to 1, 0, and the next active clock transition will make that happen. On the other hand, if your button is not 1, then your next state remains as what it was before. What was it before? 0, 1. So at every rising edge of clock, it's still present state just remains at 0, 1 because next state and present state are the same. I hope that is clear. So that's how these two processes work together. So I'm just going to come in here to just save some time. I'm going to copy this code, paste it down here, and paste it down here, because in each case I'm also checking if button is 1, except that here the next state will be 1, 1, and here the next state will be 0, 1. So that's about it. So we're more or less done with this. Let's go to the last process, which was the process for the output logic. So output logic. So the process for the output logic process, and this is only dependent on the present state, because the output is dependent only on the present state. So begin and process. So again, it makes sense to just use a case statement for this. Case present state is when 0, 0, then what will happen? Again, I'm going to go ahead and copy this a couple of times when others. Okay, so I'm going to copy this a couple of times when 0, 1, when 1, 0, when 1, 1. So when in the 0, 1 state, what do we want things to be? So I'm going to now break from everything we're doing and go and do something else before I can come and deal with this. The reason is this: we need a counter C. We need a 24-bit counter that is simply counting up. So let me go ahead and create that 24-bit counter that's counting up. I could do so within this process, but we're trying to be modular in nature. So I'm going to create a counter. I'll call it counter 24 process. It's dependent just on the clock. Begin, end, process. So I'm creating a 24-bit counter in here. So to create a 24-bit counter, I need the counter to be available across all the processes. So I can't set it as a variable because that will be local to only that process. So instead, I'm going to make it a signal. Signal CNT. Well, I called it C, so let's call it C. C in our design. So C, I like my things to line up. So standard logic vector and 23 down to 0 because it's a 24-bit counter. Good. So we have our 24-bit counter, and I'm just simply going to say that if reset, we always use our reset. If reset is equal to 0, then C, just assign the value to 0. So others, this is the easiest way to do this, 0. Okay, so just assign all the bits, make all the bits 0. Else, if we have a rising edge of the clock, then we want to increment the counter. Okay, so increment the counter if we have the rising edge of clock. So C will simply be equal to C plus 1. It's a 24-bit counter, so it will always just cycle and if. Good. It will always just keep on cycling. Once it gets to 1, 1, 1, 1, 1, 1, 1, it will cycle back to 0, 0, 0, and just keep on counting that way. So this is perfectly fine. I think this should be perfectly fine, and we should be good. Numeric standard is there, so this should work. Okay, so now we can come back and define our outputs. So in this state, we said our output should be equal to C24. So let's go ahead and define that our output is C24. So in this case, C clock out will be equal to C24. No, C23 now. The MSB will be C23. That's the 24th bit in the sequence, so that will be C23. Is that what I wrote in here? Yes. Oh, okay, sorry. I'm so sorry about that. I wrote the wrong thing in this. I should have written C23, not C24, because I'm using a 24-bit counter. Okay, so C23 is what we have in there. So I'll just copy this because it's the same thing that we have in this state. So we said we want to have the same thing in that state. Now, on the other hand, in this state, our C out should be C22. And in this state, our C out should be C21. So this should be fine. And I think with this, we're just about done with this. So I'll go ahead and hit the compile button. While I do that, I'll now look at the code once again to see if I have done anything wrong with this. Oh, I did not check this. Let's hope it does not complain because I have not written much code in here. But let's see. If it runs through, at least it will run through the syntax. Okay, so really I don't need the fitter and placer. Yes, so what's the complaint about? Clock FSM is expecting this when? Oh, okay, sorry, I left something out apparently. So it's expecting a this or a that. Oh, yeah. There's a V, there's a loose V that's not supposed to be there. I'm sorry, I think I pressed that by mistake at some point in time. So let's compile once again. And really, I should just be doing analysis and synthesis, the fitter and then assembler and all of that. We really don't need to run through any of those ones because we haven't set our assignment. We've not done our signal assignments. And okay, so another error. What's the issue here? Clock of 7% expecting case. Oh, so sorry about that. Yes. I started the case structure, I didn't end the case structure, so that will happen in a couple of places. So end case. And let's come to the output process as well. Oh, when others, I didn't even deal with when others. So when others, CLK out. So if it is anything, if it happens to be in any other state other than these, I'm just going to give out a 0. 0. Okay, good. So end case. So I think this should be fine. And let's just synthesis. Let us start running that once again. Let me look over my code. So sorry about this. Almost every time I write VHDL code, the first time I run it, it at least has an error in there. And this is just 70 lines of code. So yeah. Another error. Clock FSM cannot determine the operation. Oh, okay. So it doesn't like this. Okay, that is fine. So we'll change that. Where is it? Okay, so it doesn't like this line of code. Let's me go ahead and make this a single bit. Let's see if it will be happy with this. I know if I make it unsigned, it should work. Okay, let's see. Yeah, okay, let's just do that. Let's just do that actually. Let me just make this unsigned. I just make this unsigned so that that will definitely run through so I don't take any other time. So that'll be unsigned. This will definitely work. Now it doesn't have to be in single quotes. I could have that with an integer, and it just means that here it will complain. So standard logic of this. So I'll need to cast it as standard logic so that it does not complain, since it previously is unsigned. So sorry, just fixing this up. Standard logic, and last one, standard logic. Okay, so let's go ahead and compile this. Hopefully we should have no issue here. Let's just check this one more time. While that is going on, yes, that's about that. I think there should be no errors in this. Still an error. Type algorithm, what's it talking about? Oh, okay, so it's complaining about this. Oh, so sorry about that. Yes, it is, clock is just simply 0. It's not a vector, so it is just simply 0. Hopefully this is the last of the compilations. So sorry about this. Okay, good. So it has compiled that through and it has no problem with it. So it now says FSM1 contains no dangling pins, and then so it cannot synthesize the top level entity. But that's fine. The point is that it has compiled CLK FSM, clock FSM, and I'm good with that. So now we're done with this system. We'll go ahead and now I alluded to the fact that having button is equal to 1 using this will cause a problem for us. Now I will go ahead and continue with this project and go to ring counter and finish up FSM1. Later on, if that problem does show up, I'll point it out and then we'll come back to fix this code. But in the meantime, let's go ahead to create the new entity. Just want to copy this code at the top because I'm going to use it. And we're going to create another entity called ring counter. So go ahead and paste that up. The name of this entity will be ring counter CNC. Ring counter. Just want to save this, place it in the same file. Ring CNT. Good, save, and we should be done. Now, whenever you create a new file, it's always a good idea to come to your project and check to make sure that the file is part of the project. So all these 3 files are in the project. I didn't check that earlier. It's always a good idea. Many times, by default, Quartus places it in there, but not always. There are a few cases where it doesn't. Entity ring counter. And then let's create an architecture. Let's say count of ring CNC is begin and architecture counts. And I did not spell this correctly. That is why it's not in blue. Architecture. Okay, that's good. Good. So let's go ahead and write our code for this. Now it's going to have, so we should take a look at our design and see if we talked about that. Ring counter. So the ring counter, scroll to the ring counter. The ring counter takes 2 inputs, clock and reset, and gives 1 output, which is a 10-bit count. That's what we have at the output. So let's go ahead and write the code for that. So we have CLK and RST. RST are the 2 inputs in type standard logic, and we have 1 output, which is CNT, and that is of type out, and it is or direction out logic, standard logic. Okay, so those are our ports. Do we need to have any signal in here? Yes, we'll need to have a signal in here. Signal, since my CNT is an output, but I need to check the value of the output every time I'm going to the next state. So I'm just going to have this as signal. Signal SCNT. So this I'll just connect directly to CNT at the output. So type standard. Counter is a standard logic vector, and it is 9 down to 0. So this will be exactly the same for the signal, because I'm just simply going to connect my SCNT to CNT. Good, so that is that. Now let's have our logic in here that does the rest. I'm going to need a process that is sensitive to the clock. I need to give it a label counting. Okay, so just give it a label there. Begin end process. Good. Let's go ahead and have our code for this. Now, so I'm just going to kind of keep this relatively simple. Which do I want to use? Let's use a... what else? We might use if. Let's use if. So if SCNT is equal to 0, 0, 0... Okay, so let's do 0, 0, 0, 0, 0, 0, 0, 0, 1. I believe that is 10. I'll count that in bits. Then we're going to do something. Let's check this. 1, 2, 3, 4, 5, 6, 7, 8, 9. One more. 10. Okay, so I'm going to copy this because I'm going to use this a couple of times. Then if, oh, sorry, I need to do something. This is a little embarrassing. Okay, if reset is equal to 0, then we're going to reset counter s underscore cnt becomes others 0. Else, we now want to check for the rising edge of the clock, and okay, rising edge of clock, then, and if, so if rising edge of the clock, then we're going to do a number of things. So this will now go in there, it could be nested in there, and if, and let me end this if so I don't forget to end it, like I forgot to end the case the other time. So now, if reset is pressed, then reset the counter to 0. Otherwise, if it's in this, if it is if scnt is equal to, if s count is equal to that, then we want our s count, the next value of s count, scnt, will be, now the value I pasted, I'm just going to put a 1 at the end of that and take off one in front of it. Okay, and I'm now going to repeat this statement a couple of times, but the second time we do it will be an else if, and we're checking for 1 0, and we're going to make this 1 0 0. So now I can repeat this a couple of times. 1 2 3 4 5 6 7, I think, or is it 8? I think 8 maybe. Let's see, if I need to I'll repeat it one more time. So next state I want to check is that state. So to make sure that I am not making any mistake, I'm just going to line this up so I can see clearly. First was 1, the next is there, and then we have this over here. So it's often good to work on your alignments. That could help you to not make mistakes. If things are not aligned well, it's easy to make a mistake and not realize that one has made a mistake, and those mistakes are effectively what we call bugs, because they yield no syntax error, but they don't do exactly what you were hoping, what you planned them to do. Simply because the code was written wrongly and you didn't quite realize that that was written wrongly. And the last one here is all zeros. And then I will have an else, and in my else I will place this there and just set it to 0 0. Yep, so it will take me to that original state if no, yes. Okay, yes, that's fine. So to take me to this. Okay, good. Now I need to set what these states go to. So it goes to that, and then we're going to pick this and put a 0 there. Then we'll pick this twice and put a 0 0 there. And then we'll pick this thrice, and then 0 0 0. And then this one will be 4 times, and this will be 0 0 0. This will be 1 2 3 4 5 times, and this will be 1 2 3 4 5 times. Okay, this, something is missing. I did that more times than I should have. 1 2 3 4 5 6, and 1 2 3 4 5 6, and 1 2 3 4 5 6 7, and 1 2 3 4 5 6 7. And this, on the other hand, will be going all the way to the end. Okay, so this is our ring counter, and this is implemented. I think this should be fine. If I go ahead and run my analysis and synthesis, we should have the same error that complains about my FSM1, but then we shouldn't have any error with the counter. I'll just let this run through and see that it has no problem with the counter. Then in the next video, we'll talk about FSM1. So I just let this video run through to be sure that there's no error in the counter. So apparently there is an error in the counter. And what is the error? No semicolon at the end of this line. Let's go ahead and compile that once again. And while that is going on, is everything else fine? So actually, I don't need numeric standard for, excuse me, I don't need numeric standard for this entity. So I'll take it off once it is done compiling, if it compiles with no error. Good, so I think it's done, compiled with no error. So I'll go ahead and take off numeric standard. And so the message it gave here is just talking about top level entity once again. So that will be it for this video. In the next video, we'll focus on FSM1, which is a top level entity. And then if we do have a problem with this, we'll come back and fix this code. See you in the next one.